Okay, it's fine. So do you have any questions or comment regarding our last class? We just started process and thread, our new module. Okay, we started last couple of classes already explained in this topic. Okay. Also, as you know that in our in next class is exam, first exam. Okay, just a reminder. So you will get around, I think, you will get 1 hour, for 30 questions. All questions, are in MCQ and true false. Okay. Okay. Let's start our today's session. So in our last class, we mainly talk about the state of a process and process control block. As you know, we saw that there are several state can have a process. Start from new state as well as it can run state as well as IO or IO state, terminated state, suspended ready, suspended IO. Yeah. Also, we know about some attributes of a process. A process, it has a process ID and a program counter, of course, process state and general purpose register priority. These are the process attributes. And we know some types of scheduler. Scheduler is nothing but a functions of a operating systems. We know that long-term scheduler and short-term scheduler. Also, we introduced another scheduler in our last class. It's called the medium-term scheduler. Okay. Also, we talk about different time-related actually topic to a process. We need to know about the arrival time actually at the point of time when a process arrives at the RAM. Also burst time, we frequently use the burst time. Burst time is nothing but a total execution time of a process. And then completion time at the point when a process actually completes executions. And turnaround time, we calculate the turnaround time for different different algorithms. Turnaround time is nothing but completion time minus arrival time. We also calculate the around time is equal to burst time plus waiting time plus IO time. Summation of these three times is equal to actually completion time minus arrival time. Both either we can calculate the turnaround time. Also waiting time, the process may preempt mean that actually your CPU forcefully wait a terminate stop a process when a higher priority process comes into the RAM. Okay, this is known as the when a process preempt by a CPU, then a process needs to wait until the higher priority process completes its execution. Okay. Also IO time, the amount of time process performing the IO. Okay. So at last topic was that CPU scheduling algorithms. We categorize in there are two types of CPU scheduling algorithms. One is the preemptive scheduling algorithms, another is non-preemptive scheduling algorithms. Preemptive scheduling algorithms, CPU can preempt or stop a process when a higher priority process comes into the RAM. And non-preemptive scheduling algorithm means that CPU cannot preempt a process from its running states. Means that when CPU actually executing a process and then higher priority comes into the RAM, but the process it is that was in the running steps, it's complete its execution first. Then your OS will actually schedule a higher priority process for the CPU. Okay, this is non-preemptive scheduling algorithms. These are the two categories, and from our today's class, we will explore some primitive scheduling algorithms as well as the non-primitive scheduling algorithms. Okay. So primitive means that CPU can preempt or stop a process when the higher priority process comes into the RAM. And non-preemptive scheduling algorithms means the CPU cannot preempt a process from its running state, even if higher priority process is available inside the RAM. Okay. After completing the execution, the OS can schedule the higher priority process among the processes inside the RAM. Okay. Okay. Let's say our first CPU scheduling algorithms. It is shortest job first or SJF scheduling algorithms. Okay. Let's explore what is the SJF algorithms and say how it works. Okay, this algorithm works. Okay, let me share my as I need to draw some figures. So let me share my screen from my iPad. Okay. Okay, let me stop my video. I think it is not important. Okay, so now we'll talk about the shortest job first scheduling algorithms. Let me write it in here. It's nothing but shortest job first or SJF. Okay, scheduling algorithm. Okay, shortest job first scheduling algorithm. What does it means? Let's see what is the shortest job first algorithms. Okay, shortest job first is means that the process that's arrivals inside the RAM. The OS will schedule the process which needs the least burst or execution time. Okay, among the arrival process inside the RAM, let's say here in your RAM there are total 3 processes. For example, 3 processes inside the RAM. Let's say it needs total execution time 1 nanosecond. It needs 2 nanoseconds. It needs 3 nanoseconds. So what is the least? What needs? Which process needs the least burst time or execution time? Process P1. Okay. So process P1 will be execute first. CPU will, sorry, your operating system will schedule the process P1 first because it needs the least burst time. Okay, burst time or execution time. So this process will be scheduled first, and another is and next process P3 will be scheduled by your operating system. Okay, and next process P3 because once P1 completes its execution, then from P3, P2, and P3, which needs the least burst time, it's process P2. It needs 2 nanoseconds. So this process will be then next your OS will scheduling P2, and last process will be process P3. Okay, this is the shortest job first scheduling algorithms. Let's see one example that how and its different functionality. We'll see from one example that how the list SJF works. Okay. Okay. Let me see you one example from SJF. Also, here you need to know that that one criteria is for it's actually execute nothing but the which process needs the least burst time, and another criteria is that it is a non-preemptive scheduling algorithms. Okay, this SJF SJF is a non-preemptive scheduling algorithm. You need to know about this. You need to take notes about the shortest job first scheduling algorithm. There is two properties. First one, that among the arrival process inside the RAM, which will execute the least the process that needs the least burst or execution time. Second one is this is a very important criteria as well. The SJF is a non-preemptive scheduling algorithm. As you know, that non-preemptive means that, let's say, for example, let's say this is process P1 needs 5 nanosecond, P2 needs 2 nanosecond, P3 needs you now your OS actually from this 3 process, which one will be scheduled by your operating systems. From here P2 needs the least execution time, because I changed it. P1 needs the 5 nanosecond and P2 needs the least burst time. So P2 will be scheduled by your operating system and it will be executed inside the CPU. Okay, P2 will be executes among these 3 processes. And when it's during this execution time, let's say another process P4 comes to the RAM. So it needs 1 nanosecond. So currently you see here, this one is the needs the least burst time or execution time. But here P2 is already running because due to the SJF, due to the non-preemptive properties, P2 is currently in execution mode. So your CPU cannot stop or preempt this P2 process from its running state. Okay, so your P4, even if it needs 1 nanosecond, it needs to wait until the P2 completes its execution. This is the non-preemptive. Okay, once it's from this among this process, your OS is scheduled the process that needs the least execution time. And once it's scheduled by for the CPU, your CPU cannot preempt this process until it completes its execution. Okay, this is the non-preemptive properties. Also, SJF is a non-preemptive scheduling algorithm. Okay, these are the 2 properties. Let's say one example how your SJF algorithms work. Let's say we have total 5 process. A process should have, of course, the process ID. Let's say process ID. I will draw a actually table here. This process ID. Here is arrival time of a process. Arrival time means the process comes to the RAM. Okay, this is arrival time of a process. And third is our burst time or execution time. Burst time or execution time. Okay, this is your okay, this is your let's say you have total 3 process P1, P2, process ID, P3, P4, and P5. Okay, we have total. Now we are actually exploring the SJF algorithm. Okay, and arrival time is process P1 arrive at two time units. It can be any times. Let's say 2 time unit means it can be nanosecond, millisecond. Okay, whatever it is 2 time units. Any 2 times unit, any times. This unit can be anything. Just I just write the 2, just a number. I just mentioned a number. 2 time units. It can be nanosecond or millisecond. Okay, millisecond or microsecond, whatever you consider. Okay, it's, let's say 3. at time unit 3, and process P3 arrives at time unit 4, and P4 arrived at time unit 6, and P5, process P5 arrived at time unit 8. Okay, this is the arrival time for process P1, P2, this is for P3, P4, and P5. Okay, arrival time means this process comes to the RAM. Process comes to the RAM from your SD, from your disk, hard disk. Okay, this is the arrival time. And what is the execution time for this process? Let's see. Process P1 needs 3 time unit, means a 3 microsecond, nanosecond. It can be any time unit. For to complete this example, it is fine. So it takes 2 time units, and it needs 3 time units. It's 1, and it needs 2. Okay, let's say nanosecond. Okay, let's say nanosecond. Okay, nanosecond of, yeah, nanosecond. It is fine. Okay, now let's go a Gantt chart. Gantt chart, execution chart for this process, how it's work. Here you need to actually look at this point, look at this part, that how this process this process will be scheduled by your operating system if you consider the SJF. Okay, let's now I'm drawing the process Gantt chart. Okay, this is time unit 0. At time unit 0 to at 0 there is no process. Also time unit 1 there is no process arrives at the RAM. There is no process arrive at the RAM. At time unit 2, the process P1 arrived inside the RAM. So 0 to 2 time units there is no process inside the RAM, means that in this time your CPU will be idle. Okay, CPU will be idle because there is no process inside the RAM until 2 time unit. Okay, after 2 time units, we see process P1 inside the RAM. So what your CPU will do? There is only one process, because process P2 comes at 3 time unit. So there is one process P1 at arrived at 2 nanosecond, 2 time units, and then your your operating system will schedule the process P1. It is in running state now. So it will also, it is, it is non-preemptive algorithm. So of course it will run till 2 time units. So 2 to 4, your 2 till 4. Okay, it needs the 2 time units. So 2 till 4, process P1 will be executed by your CPU. Oh no, sorry. This is 3 nanosecond. 3 times unit. Okay, it's consider nanosecond, it's nanosecond, microsecond, it's microsecond. Okay, 3 time units. So it will complete the till 5, 2 till 5. Okay, because it started 2 time units, and it will be stop at 5, because it takes 3 time units to complete its execution. So in this time, your CPU will execute process P1. And now time unit is 5. So now let's see how many process you inside the RAM. So process P3 arrives at time unit 3, means that at this time your process P3 arrives at the RAM. Also process P3 also, sorry, P2 is arrived at the RAM. Also P3 arrived at time unit 4. So now your clock time is 5. So process P3 is also inside the RAM. Okay, P4, it will arrive at time unit 6. Now it is 5. So so process P4 is not still inside the RAM. So currently process P2 and P3 inside the RAM. Okay, so from these 2 process, which process will be scheduled by your CPU from these 2 process, P2 and P3? From here, you see this SJF algorithm. So it will schedule the list, the process that contains the least burst time or execution time. Here, this P2 needs 2 nanosecond or 2 time units, any time units, and your process P3 needs the 3 nanosecond or any time units, 3 time units. Here it needs the 2 time units. So so P2 actually it needs the less burst time or execution time process P3. So P2 will be scheduled by your operating systems, and it will execute till 2 time units. So 5 plus 2 will be 7. Will be 7. Till 7, P2 will be executes. Okay. And then at 7 time units, how many process will be inside the RAM? P2, this 2 is completes its execution. Now clock time is 7. Here is 4 and 6. Yeah, 6. P4 is inside the RAM. It will come at time unit 6. Means that around this time it comes inside the RAM, and process P5 will be arrived at time unit 8. So still process P5 is not inside the RAM. So only 2 process P3 and P4 inside the RAM, because current time is 7 time unit. Also here is arrival time is 4 and 6. So these 2 process inside the RAM. So from here, which process will schedule by your CPU the process that needs the least burst time. Here P4 needs one time unit, P3 needs the 3 time units. So P4 will be scheduled by the operating system. So P4 will be executes. So it will take 1 time unit or 1 nanosecond. So 7 plus 1 is 8. Then it completes its execution. Now clock time is 8. So how many processes now inside the RAM? This series completes. So process P5 arrives at time unit 8. So now clock time is 8. So process P3 and P4 is currently inside the RAM. So from this P3 and P5, which process will get the priority to execute? It takes process 3 needs the time. It needs 3 time units, and process P5 needs 2 time units. So process P5 will be scheduled. So it needs the least burst time or execution time. So till 10, 2 time units, 8 plus 2 plus 10 time units it will execute. And then we have only one process, P3. P3 needs total 3 time units. So P3 will be executed still in here, till P3. Okay. This is the execution Gantt chart for this process table, if we consider the SJF algorithms. Okay. So do you have any question or any confusion regarding these SJF algorithms? Okay, so let's explore some other features for these SJF algorithms. Let's calculate some time process related time, we can say from here. Let's calculate the completion time of a process, or CT, completion time of a particular process. And next we'll calculate the turnaround time and waiting time, and some other parameters we'll calculate from these algorithms. Okay, now we calculate that. First we calculate the CT or completion time, and then turnaround time, and next we'll calculate the waiting time of a particular process. Okay, so let's see. Completion time is nothing but actually which from this Gantt chart you can figure out the completion time of a process. Let's say process P1, at which point it completes its execution. From here you can see at time unit 5 it completes its execution, process P1. From here you can see time unit 5. So it's completed time unit 5. Next is process P2, at which point it completes its execution. It's time unit 7. And next is process P3. process where at which point it completes its execution at time unit 13. Okay, 13. Next is process is 13. Okay. Next is process P4. P4 completes its execution at time unit 8. So 8 is execution completion time, and process P5 completes its execution at time unit 10. Okay, 10. Okay, this is the completion time of a process. From this Gantt chart, you can easily figure out. And next is the turn around time. You know this TAT or turn around time. TAT is equal. I already mentioned that completion time minus arrival time. Arrival time. Okay, completion time minus arrival time. Also, another equation is turn around time is execution time ET plus execution time or burst time. It is the same thing. Execution time. Next is IO time plus another is waiting time. Okay, this three is nothing but equal to completion time minus arrival time. It means that how long a process inside the RAM. Okay, how long a particular process inside the RAM. This is the total turn around time. Okay, from here we have this. We know this CT. Also we know the arrival time. So from here we can easily calculate the turn around time. We CT is 5 and arrival time is 2. So 5 minus 2 is nothing but 3. For this for process P1, turnaround time for process P1, and here completion time is 7, arrival time is 3, so it is 4, and here is turnaround time is 9, 13 minus 4, here is 8 minus 6, nothing but 2, here is also 10 minus 8, it's also 2. Okay, this is the turnaround time. So how to calculate the waiting time here? Also let's one thing we need to make assumption is that here is IO time. IO time is 0 for all 5 processes. Okay, IO time is 0 time unit for all process, means that in this process, all these 5 process, it doesn't need any IO during its execution, means that it doesn't access any IO devices like keyboard, as well as the it can be printers, or it can be mouse. Okay, or others. Okay, so let's assumption this IO time is 0. So TAT, we know that execution time or burst time plus waiting time. So from here you can see this waiting time is nothing but a turn around time minus ET, execution time. Okay, from here we can get this. So we can calculate the TAT. We know this already, TAT, turn around time. Also we know this execution time here in this column. So from here we can calculate the waiting time. Waiting time is 3 minus 3 is 0, 4 minus 2 is 2, 9 minus 3 is nothing but 6, and 2 minus 1 is 1, 2 minus 2 is 0. This is the waiting time for a particular process. Okay, for a process P1 actually arrives at 2 time units. Also it gets the, from here you can see also it gets the CPU at time 2 as well. Okay, so it doesn't require to wait inside the RAM. So waiting time is 0. Also, if you consider this process P4, P3 arrives at time unit 4, but it actually gets the CPU at time unit 10. Okay, at time unit 10, it gets the CPU at time unit 10. Okay, from here 10 minus 4 is also 6. Okay, from here you can also, from this Gantt chart, you can also decide that how long the turnaround time for a particular process. Okay, now let's calculate another properties. It's called the schedule length. I just mentioned the schedule length. Okay, let's calculate the schedule length. Okay, schedule length is nothing but, here is we currently talk about the total 5 process. So when it completes the all 5 processes, its time unit 13 minus the starting time of actually when at the starting time when a process actually start for execution. Okay, from this among this process, the starting time of the of a process. Okay, of a process. Total completion time is 13 at point 13 completes the all processes, and it was started at time unit 2. So 13 minus 2, this is the total schedule length for this 5 process. So 11 is the schedule length uh, for this example. Okay, for this example to complete this 5 process. Okay, this is the schedule length. Another is throughput. This is also very important parameters we'll use in our later section as well, to measure the efficiency of CPU scheduling algorithms. This is by using the parameters called the throughput. Okay, throughput. Throughput, we can say this number of process divided by schedule length. Okay, what does it means? Number of process divided by schedule length means that uh, per unit time, how many process actually executes means that if you consider this a nanosecond per every nanosecond, how many process executes. Okay, or if you consider this time unit as microsecond, every microsecond, how many process was executed. Okay, this is the nothing but the throughput is equation is number of processes divided by schedule length. Okay, schedule length that we calculate here, schedule length here. What is the throughput? Number of process we consider 5 divided by schedule length is 11. Okay, 11. This is the throughput. It is nothing but process unit is process divided by unit time. Okay, unit time. Okay, process divided by unit time. Okay, throughput. Let me write in here. There is throughput is nothing but number of processes is 5, and we have total schedule length was 11. So 11, this is process divided by unit time unit. Okay, time unit. Okay, so it means that every microsecond or every nanosecond, how many process was completed. Okay, this is also we can, from this throughput we can measure the efficiency of we can evaluate the performance of a particular scheduling algorithms. In our later section, or in our later classes, we will see that how to evaluate the different uh, different scheduling algorithms, or comparison of different scheduling algorithms. Okay, that time we frequently use this throughput. Okay, so you can take notes for what is the throughput. Also TAT, ET, schedule length also very important parameters. Okay, so this is the shortest job fast scheduling algorithms. And okay, so before I move to our next algorithms, scheduling algorithms, do you have any questions or comment regarding the SJF? Okay, if no, let's move forward to the another scheduling algorithms. It is called the SRTF. SRTF, shortest remaining time scheduling algorithms. Okay, let's see what is the SRTF. It is, let me write in here, shortest remaining time time first, or here you can say that SRTF, okay, SRTF scheduling algorithms, okay, SRTF scheduling algorithms, let's say algorithms, okay. Okay, we'll talk about the SRTF, okay, in our in this section, okay, we'll talk about the SRTF, shortest remaining time first scheduling algorithms, okay, SRTF algorithms. Okay, let's check this. What is the SRTF algorithms and how it works? Okay, let's some definition for SRTF, or we can say these properties of SRTF. SRTF actually among the arrival process inside the RAM, OS will schedule the process which needs the shortest execution time. It is almost similar to the SJF that we learned previously, but it is preemptive. SJF is preemptive, non-preemptive scheduling algorithms, but SRTF is the preemptive scheduling algorithms. Okay, preemptive scheduling algorithms. Also, you know that what is the preemptive scheduling algorithms. Okay, SJF is non-preemptive scheduling algorithms. Also, SRTF, we can say that it is a preemptive version of SJF. Okay, it's a preemptive version of SJF. Okay, what is preemptive scheduling algorithms? So when actually shortest actually let me explain it another way. So let's say that you have already your CPU executes a process when a shortest burst time, or when a shortest execution times process inside the RAM, then your CPU will stop the currently execution process. Okay, currently executing process. Okay, currently executing process, CPU will stop, and then it will allow your OS will schedule the CPU for the higher priority process. Okay, higher priority means nothing but the process that actually contains the shortest burst time. Okay, one more thing I have to mention here: both SJF and also SRTF is they both are the priority based algorithm. Priority means that the process that requires the lowest burst time or the least burst time. Okay, both are the priority based algorithms. Okay, but SJF is non-preemptive, SRTF is preemptive scheduling algorithms. Okay, let's do one example, then it will be more clear that how SRTF work. Okay, let's draw again one. Also, one note is that it is preemptive. It is preemptive version of SJF. Okay, SJF. This is one note in here, and let's see that. Let's calculate the completion time as well as the turnaround time and waiting time, also Gantt chart and schedule length and throughput for some particular process. Okay, some processes. Okay, let's consider. Let me draw again one process diagram. Here we have the process ID. Let's say this column is for process ID. We have total 6. Let's consider currently we have total 6 processes, and this ID is P1, P2, P3, P4, P5, and P6. We have total 6 processes, and here we have total 6 processes. Okay, let's their of course their arrival time, or AT, you can say arrival time. Process P1 arrive at 0 at time unit 0 and 1. This is 2, 3, 4, 5. Okay, and their execution time or ET, let's say ET is, it needs 7, 5, 3, 1, 2, 1. Okay, this execution time. Okay, we'll calculate the completion time CT and also turnaround time, and also waiting time among these processes. Okay, we'll calculate this by when we apply the SRTF algorithms. Okay, so let's draw the Gantt chart for, let's draw a Gantt chart for this for SRTF algorithms. Let's see how it works. So this is the starting point for Gantt chart. Okay, we'll start. Okay, at time unit 0. Sorry, let me remove it in here. Let me make it a little bit smaller. At time unit 0, let's me draw in here. At time unit 0, which process is there any process inside the RAM? Yes, at time unit 0, P1 inside the RAM. Okay, inside the RAM, and its execution, it needs the total 7 time unit to complete its execution. Okay, it's arrived at 0. So yeah, at time unit 0, there is no other process. So your operating system will schedule the CPU for process P1. Okay, let's see, process P1 is scheduling here, and it will complete still one time unit at 1. Okay, it will complete at one time unit. So at one time unit, so it's complete still 7. Now it's 6 is 6 time units required to complete its execution at one time unit. So every time unit you need to check this other process is currently available or not, because it is preemptive algorithms. Okay, it is not like a SJF. It is not a non-preemptive scheduling algorithm. It is preemptive scheduling algorithm. So now you look at in here, at time unit 1, process P1 and P2 both are inside the RAM. So here your P1 requires 6 time unit to complete its execution, but your P2 needs total 5 time units to complete its execution. So which one will gives the priority for SRTF? SRTF will gives the priority for process P2 because it needs the least burst time. So it is preemptive algorithm. So your CPU will stop the execution process P1 and your operating system, because your operating system will schedule for the process, the higher priority process P1. Okay, so from this running state to it will go for this ready state. From this running state, it is stopped from this running state, and P2 will actually gets the CPU because it needs the least burst time. So it will execute still one time unit and 2. So now it is 4. So after 2 time units, at 2 time units, how many processes inside the RAM? Process P1, P2, P3, all are inside the RAM. Okay, all are inside the RAM because P3 process P3's arrival time is nothing but 2 time units. So currently clock is in 2 time units. Okay, so now from here, which process will be scheduled? The process P3, it needs 3 time units. P2 needs 4 and P1 needs 6. So P3 will be scheduled in next, because it needs the lowest burst time, shortest remaining time. Okay, it needs the it needs the lowest burst time or shortest remaining time, whatever it is. It is good. So now you have total P3 will be executes, P2 will be stopped. Also previously P1 also stopped, so it will execute still one time units it will be 3, and now it is 2. It needs the 2 time units. So let's check this after 3. How many process inside the RAM? Now we clock is in 3. So 0, 1, 2, 3. At 3 time unit process P4 also inside the RAM. Okay. So all 4 processes are currently inside the RAM. So among this process, which needs the least burst or execution time, P1 needs 6, P2 needs 4, P3 needs 2, and P4 needs 1. Okay, 1. So this is the list. It needs the least execution time. So your operating system will schedule for this process P4. Okay. It needs total 1 time units. So 4. After 4, it completes its execution. Okay, it completes its execution. It needs only 1 time unit. Okay. 1 time in 3 to 4, 4 to 3 means 1 time minutes. It completes executions, and now time is 4. So from here we can see that how many process inside the CPU inside the RAM. So now P1, P2, P3, and P5. At 4, P5 is available. So P4, P3, P5. Here is one thing you take a note that here is one thing interesting. Here the two process. Here you can see the two process P3 and P5 both needs the 2 time units. Okay, these are the same time unit. So from here, which actually process will get the CPU first? Operating system will get the CPU first. Okay, it can be any process, but you can develop your algorithms like that. The process which comes inside the CPU first, that will get the priority when execution time is similar, because P3 comes first. P3 comes before the P5 process P5, so P3 should get the priority. Okay, so P3 will be executes for 1 time units, because it needs 2 time. Still, it needs the 2 time units to execute the process. So P3 will execute here. It needs 1 time unit, so 5. So it already from 2 to already 1 time unit is complete, so 1 is remaining. So after 5, how many processes inside the RAM? Now we have total P1, P2, P3, P5, and P6. All are inside the RAM. Okay, all are inside the RAM. Here P3 needs 1, also P6 also needs 1 time unit. So, but P3 actually it came fast inside the RAM. So your OS will give the priority for process P1, because it needs only 1 more unit time unit to complete its execution. So P3 will execute first, and now 6. So P3 is completes its execution currently. P3 is done. Now from this process, we see from this process you can see that P6 needs the least burst time or execution time. So P6 will be scheduled by your operating system. So P6, it needs one time unit. So it's completes the execution. P6 is done. Now we have total P5, P2, and P1 till 3. P5 needs 2 time units. P2 needs 4, P1 needs 6. So P5 will get the priority. It needs least burst time. So P5 and P5 will take total. Okay, once every process inside the RAM, then actually it behaves as like a SJF. Okay, all process is now currently inside the RAM. So you know that P5 currently will get, if it is execute 1 time units, so it will be 1. So it will get this again its priority. Okay, to execute. Okay, once every process inside the RAM, then it's your SRTF is behave like an SJF. Okay, once all process inside the RAM. Now P5 again, you can check this 8, and then it takes 1 time unit. It needs 4, it needs 6. So again it will the P5 this process, and a similar process its priority. Okay, so it will execute P5 till 9. So it's completes its execution. So now we have total P1 and P2, these two processes, okay, inside the RAM. So of course, the P2 will get the priority. It needs 4 time units. So P2, so it will execute still 4 time units, 9 plus 13 till 13. It completes its execution. And next P1 will only one process P1. It will execute till 6. It needs total 6 time unit. So 13 plus 6. It will all process will complete at 19 at time unit 19. Okay. So here every process will be completed. Next, let's compute the CT as well as the TAT and WT for SRTF algorithms. Okay, let's compute that how it looks like. For CT completion time, we can actually go back from this way. Then we can find this completion time. Let's say P1 in here. P1 first last appearance for P1 as time unit 19, so it's completed at 19 time units. And then P2 in here, it's completed 13 time units. And then P3, let's complete the P3, yeah, last time is 6 here. And next is P4 is in here, okay, 4 at 4 time units. And then P5 we have found in here last time. So P5 it is in 9. It is in 9 time units. And next is P6. Okay, where it is in 7 at time unit 7 is complete. Okay, at time unit 7. Okay, from here you know that what is that TAT, turnaround time. You can calculate the turnaround time. Turnaround time is nothing but completion time minus arrival time. Okay, completion time at 19 minus arrival time is 0, means the 19. 13 minus arrival time is 1. 13 minus 1 is 12. And 6 minus 2 is 4. 4 minus 3 is 1. 9 minus 4 is 5. 6 minus 2. Okay, this is the turnaround time for each processes. And let's see what is the waiting time. Waiting time, we can again let's see that we can calculate the TAT. Like TAT is nothing but execution time ET plus IO time plus WT time. Okay, waiting time. Let's say no process actually goes to IO for this actually all 5 processes. No process actually it doesn't needs to go for IO. So IO time is 0. Let's assumption this IO time is 0. So next, what will be the WT? WT is TAT minus ET, execution time. Okay, TAT minus ET. Okay, I can type in here. You know about this TAT minus ET. So here you can calculate what is the waiting time. TAT minus execution time. 7 minus 19. So waiting time is 12. Nothing but is 12 in here. 12 minus 5 is 7. 4 minus 3 1. 1 minus 1 0. No waiting time. 5 minus 2 is 3. 2 minus 1 1. Okay, this is the waiting time. So from here also you can see that what is the schedule length. Schedule length is nothing but schedule length is nothing but 19 minus 0 is kind of here is stop at 0 and start at time unit stop at time unit 19, and it was started at time unit 0. So 19 minus 0 is nothing but 19. The throughput, what is the throughput in here? Throughput equals here number of process, total number of process 6, number of process divided by schedule length 6 minus 19. Okay, this is the throughput, okay, for SRTF. Okay. So this is not slight different. This two algorithm is different. One is the preemptive, another is non-preemptive algorithms. Okay, SRTF is preemptive algorithms, version we can say preemptive algorithms, but SJF is non-preemptive scheduling algorithms. Okay, this is the two algorithms from this from preemptive as well as the non-preemptive. Example of preemptive and non-preemptive scheduling algorithms. So let's see. We have time little bit. Our next algorithm is first come first serve algorithms. First come first serve. Okay, algorithms. Okay, let's check the what is the first come first serve algorithms. The process which comes in. So let me. Okay, sorry. I have to write. The first come. Next algorithm is first come first serve scheduling algorithm, or here we can say FCFS. Okay, FCFS. Okay, first come first serve scheduling algorithms. Okay, this is another algorithms, scheduling algorithms we need to learn. It's let's see what is the first come first serve actually it means. Okay, the process which has the least arrival time will be scheduled first. Okay, this is from here you can understand the first come, the process which comes first inside the RAM will be served first, or will get the CPU first, or will schedule your OS will schedule the process which has the least arrival time. Okay, which comes first inside the RAM. Okay, also this is first come first serve is also a non-preemptive. Okay, you have to know you have to distinguish, or you have to know this, that which are the non-preemptive and which algorithms are the preemptive algorithms. Okay, so far we get the SJF and FCFS is non-preemptive scheduling algorithms. Okay, whether the SRTF is preemptive scheduling algorithms. Okay, FCFS is non-preemptive scheduling algorithms. Also, it is not a priority-based scheduling algorithms. Okay, why you can say that? Okay, the process which comes first, and our operating system also schedule these algorithms. This actually process first, schedule the process first. So why it is not a priority-based? Actually, the process which comes first inside the RAM, then it is not a property for a process. Okay. For example, in SJF, also SRTF, the process which has the least burst time or execution time, this is a property of a process. So this is a priority based. But it is here simple. The process which comes first inside the RAM, also this is not any properties for your process. So it is not a priority based algorithms. It is simply the process which arrives at the RAM first. It is your operating system will schedule these algorithms, or sorry, this process first to execute. Okay, so this is not a priority based algorithms. It is a non-priority based scheduling algorithm. So here is two things you have to know, that it is non-preemptive scheduling algorithms. Also, it is not a priority based scheduling algorithms. The process which comes first inside the RAM will be served first. Okay, it is not a property of a particular process. Okay, this means the first come first serve algorithms. So before okay, let's also we'll explain the first come first serve algorithm by using different process, as well as we'll calculate the arrival time, execution. Sorry, we'll get the arrival time as well as the burst time from this process. From there we'll calculate the Gantt chart as well as the completion time, turnaround time, waiting time, also response time that we calculate the in our actually last two algorithms. We'll do this, but today we are almost running out of time, so let's stop here. In the next class we'll talk about the first we'll actually see one example for FCFS algorithms. Okay, so before we go, do you have any questions or comments regarding today's class as well as our next class is your exam, first exam, okay, mid exam, okay. So in our next class we don't have any classes. I already mentioned that we don't have any class in Thursday. Okay, Thursday is your first exam, so we will actually sit for the exam on the exam. Okay, we don't have any class. Okay. Okay. So let me share. Let me stop my share. Yeah. Okay, I think if you don't have any questions, so we can stop here. So have a good evening and see you next exam.